In the last video, I talked about the Heisenberg's uncertainty principle and how there is a corresponding uncertainty relation for time and energy that could be used for electromagnetic radiation. But in this video, I'll describe an example of how we could use this time-energy uncertainty relation. Let me write this out again. Delta T, delta E is roughly equal to Planck's constant. Now, one example where this relation is often used is for line spectrum. So if you remember, say for the hydrogen atom, where we have a proton, and then there are these orbits of allowed radius. Okay, and that when we have transitions, when electrons move from say a higher to a lower orbit, it emits a photon. Right, the loss in energy of the electron is converted into the energy of a photon, and this this photon that is emitted, we can imagine that we can observe it on a spectrum, and for transitions to the second orbit, from higher orbits to the second orbit, we have already seen in earlier videos that the frequencies are within the visible spectrum. And in particular, I have often talked about 4 of the lines that are more obvious. And within the visible spectrum, there might be 1 or 2 other weaker lines that I've not shown. Right, now, so this photon that is emitted would show up as lines on the spectrum, okay, because they have a definite frequency. They have a very definite frequency. So one line represents one frequency, this line is another frequency, that line is another frequency, and there are no frequencies in between. And for example, if I think of this, let's say this direction or this line as the lambda axis, as I've often written it in the past videos, then the value of this wavelength, of the red line's wavelength, is 656.3 nanometer. Okay, so this is what we already know. Okay, now let's see how this is related to the uncertainty relation. So let me come back to this line. Okay, for this example, I'm just going to look at this line. So as I was saying, this line, as I have always often said before this line is a line because it comes from light with a particular frequency, with a definite frequency. Now, but if we think back at what I described in the past video, if I have a light, let's say a light of particular frequency, a wave of a particular frequency actually, if it is a very precise, very definite, a very just a single frequency, it must mean that this wave must go on forever. Okay, so that the period or the wavelength would keep repeating itself. It must be a wavelength that goes on forever if it's a single frequency. But in fact, in real life, we know that that's not possible. The wave, even if it's emitted by the atom, must only last for a short time. Right? After emitting it, there will be no more light. Okay, there will still be light on the spectrum because it will keep getting light from many different atoms. All right, but for each atom, after it has emitted that photon, that's it. The electron would have fallen to the lower orbits and it stops emitting until such a time that that electron gets maybe knocked to a higher state again by some other atoms or electrons. So with this idea, with this picture, we can imagine that this whatever wave or the wave, let's say the red color photon or the red color wave that is emitted by the electron falling to a lower orbits, this red color wave in practice, it must surely last for only a certain time. It's not going to last forever. Okay. So there is a certain delta t. There must be a certain time of this wave. A certain time for this wave. Now, if there's a certain time for this wave, then it must have a certain energy range, as I described in the last video, that is related to the delta t by this uncertainty relation. So what it means is that this finite time of finite duration of the red color wave, the red color light wave, this finite duration must correspond to a certain range delta E of photon energy or frequency, right? HF is the energy. So if there's a certain range of energy, it means that there's a certain range of frequency. And therefore a certain range of wavelengths. And what this means is that this very narrow line that we see on the line spectrum, right? We would see a clear red line if we actually look at the hydrogen spectrum. But that very clear and sharp red line does not have zero width. It does not have zero width. It has a certain thickness in the line. A certain thickness. Okay. And it's very narrow, but it still has a thickness. So what it means is that there is a certain range of wavelengths in this red line. Very narrow range, but still it's not a single wavelength. There's a range of wavelength. And that range of wavelength is associated with the range of frequency, which is in turn associated with the finite duration of this wave that is emitted by the atom. Now the measured wavelength, let me write this down. The measured range actually, of wavelength, I'll call it delta lambda, is about 0.001 nanometer. Okay, so this is very very small compared to the wavelength itself, which is, this wavelength is 600 over nanometers. So this is 0.001. So we are talking about 1 over 1 million of the wavelength, roughly. Okay, so an extremely narrow line. So what I'd like to do is this. Now through other experiments, through other types of experiments, it has been known that when an excited hydrogen, that means when the electrons in a hydrogen atom gets excited to a higher state, right, it will fall back to a lower state after a certain time, which we call the lifetime. The lifetime of the excited state. So that's the hydrogen atom. So from other experiments, other measurements on hydrogen, it has been measured that the lifetime of the excited state is about 10 to the power of -8 per second. And that's must be about 10 nanoseconds. Meaning that after the electron gets excited, then within a time of about 10 to the -8 seconds, that excited atom would fall back down. So what we could do for this example is that we can think about the duration of this red light that is emitted. We can think about the duration as roughly equal to the lifetime of the excited state. Okay, so this is roughly equal to delta t. So it stays up there for about this time and then comes back down. Okay, now it's a bit difficult to imagine the mechanism, how exactly it produces a wave like that as it comes down. So we are not going to be going to worry about that. Okay, we just know that there is a certain width, a certain range of wavelength that has been observed in the spectrum, and we deduce, right? We reason that it must be due to a finite duration of the wave itself. Okay, and we associate this duration, or we try and see if we can associate. We're going to try and see if we can associate this duration with, say, the lifetime of the excited state. So, therefore, assuming that the duration of the red light wave emitted by the atom is about the same as the lifetime of the excited states of the hydrogen atom, we can now use the uncertainty relation to calculate the range of energy, and from there we should be able to find the range of frequency and therefore the range of the wavelengths. So following from this, we have delta E, the range of energy, is about h over delta t. Now, we know delta t is this, and h we know is 6.63 times 10 to the power of minus 34 joule second. So with these two numbers, we can calculate h over delta t, and the answer, let's see, the answer is 4.136 times 10 to the power of minus 7 eV. I'm giving that in electron volts. And the energy from this wavelength, we can also find the energy if we want. Okay, so the energy would be HF, and we know that F is C over lambda. So we know over lambda. So we know H is this. We know lambda is that one, that value, and we know C. C is 2.998 times 10 to the power of 8 meters per second. Okay, so we have all these values, and we can find an answer. 1.889 eV. So with these two values, we would be able to find the corresponding line width. Okay, because we know that E and F are just related directly. It's just H over F. So all I need is to divide each of this by F. Okay, if I divide each of this by F, by H, okay, that will give me delta F. From delta E, if I divide by H, I'll get delta F. E, if I divide by H, I'll get F. Okay, and then the ratio between these two will give me the fractional change in the frequency, which will be equal to the fractional change in the wavelength. So without going through the details, right, I'll just state the results of what I found. What I found from this calculation is that delta lambda is equal to 0.0001 nanometer. So this is the result that I got by using the lifetime of the excited states. Okay, if the atom just takes about this amount of time to generate this wave, let's say the atom generates a wave of this time, right, that lasts for about as long as the excited state, then 0.0001 nanometer is the kind of line, the kind of width of this spectral line that we would expect to see. So this is one important and common application of this particular uncertainty relation that relates time and energy. Now let me just finish off by pointing out one obvious issue. If you compare this with this, now this is calculated from the lifetime. Lifetime of the excited states. This one, however, let's see where they come from. This is measured. This is okay. This is measured. Now, if you look at these two numbers more closely, you see that there's an extra 0 here. Right, this is 0.0001, that's just 0.001. It's got 1 0 fewer. Okay, so they're obviously different, very different in fact. The measured value is 10 times bigger than this calculated value. So what's happening here? Does it mean that this is wrong? Not really. What people have also found, right, through further calculations and measurements, is that there are something else. There are lots of other things going on in the hydrogen gas, right? In a heated hydrogen gas or hydrogen gas with bombarded by a beam of electron, as it produces these colors, these frequencies, right? And one of the things is that these hydrogen atoms in the gas would obviously not be at rest. They would be moving around, bouncing around. Especially if they get hotter, they would move around quite fast. Now, this motion has an effect on the wavelength. It's something called Doppler effect, which you might have noticed if you stand next to a passing train. Right? When the train comes closer to you, you hear a higher frequency of the sound of the train or whistle. As the train goes away from you, you would hear that the same sound becomes lower in pitch. So that's a Doppler effect, meaning that the movement of the atom away from or towards maybe the detector will cause a slight change in the wavelength. And the calculations and estimations using the velocities of the atom has shown that this effect, due to the movement of the atom, is big enough to cause an increase in the width, meaning the range of this wavelength or frequency. Right, it's large enough to cause this amount of the measured value of the wavelength range. Okay, so this estimation from the lifetime has itself been confirmed independently by other types of measurements.